University of Colorado. Come give us a seminar today. Mitch has worked on many different topics, but today he's going to talk about some of his latest work, which is on quasistars.
Okay, thank you. I'm going to talk about a project that's sort of been evolving over the last 3 years. I started it when I went on sabbatical to Cambridge as a way of trying to get Martin Rees actively involved in a project, in a collaborative project with all the other things he has to do. It worked reasonably well. And the problem that I'm going to talk about is the formation of the first seeds of supermassive black holes. So I'm not going to tell you the entire history of supermassive black holes, but some ideas about how the precursors of these black holes might have developed and started their rapid growth. The collaboration started with Martin and Martin Voluntary, who's now at Michigan, who was at Cambridge at the time, and also now includes Eleanor Rossi, who's now in Jerusalem, Phil Armitage, and Isaac Schlossman. The reason for worrying about how the first supermassive black holes formed is really twofold. First, we know that black holes today are extremely common. In supermassive black holes in the centers of galaxies are extremely common. There's roughly one per present-day large galaxy. But also we know that they had to have, at least some of them, had to have formed and grown to rather large size by fairly early in the universe, because we see quasars with black holes. I think I'm going to switch to the physical pointer. We see quasars with black holes as massive as 10 to the 9 solar masses or more, already at a redshift of 6, which means about 1 billion years after the Big Bang. And so black holes had to form early and often. And if you try to create these very large black holes starting with much smaller seeds, you run into some pretty severe constraints on how you have to do that. You have to start the process early, but even if you start the process relatively early, these black holes have to grow by accretion almost continuously if they're limited to the Eddington limit. Even if you do that, if you start with seeds that are too small, it still is rather difficult to get up to 10 to the 9 solar masses by a redshift of 6. And so that has been a major challenge in trying to figure out how these black holes form. But even, and in fact there are two schools of thought for approaching this problem. One is that the seeds of these black holes were really stellar mass black holes, the remnants of POP3 stars, which most people believe were probably quite a bit larger than ordinary modern stars, but still in the stellar range of hundreds of thousands of solar masses. And the other possibility is that they formed from some much more exotic concentrations of gas, sort of a direct collapse of very large gas clouds giving you a very big head start. Now, worry about this problem actually started long before we realized how common supermassive black holes are in the universe, because 30 years ago we already knew, and this problem actually, what I'm going to focus on today is the direct collapse of gas scenario, which really is a scenario in which the first big black holes formed from the collapse of supermassive stars. Okay, so let me just present that. This problem goes back long before we knew how ubiquitous black holes are, because 30 years ago we knew about active galaxies. We were already pretty convinced that black holes were at the hearts of these. And back in the late 1970s, Martin Rees devised a flow chart of all the ways that he could think of for black holes to form. And the purpose of this flow chart was to show that no matter what initial conditions you start with, ordinary main sequence stars, what we would now say are POP3 stars, or gigantic amorphous gas clouds, no matter what you do, you end up with something that can't support itself against gravity, that can't disperse itself, and therefore ends up as a massive black hole. I guess there are a couple of places here where they can disperse themselves, but nevertheless, you sort of see where things are going. Now, the reason I'm showing this is that in the 31 years since this chart was first created, it has evolved quite a bit, but much more in style than in substance. People are still studying essentially every single one of these possibilities in the flow charts, and no definitive conclusions have been reached. That same year, this chart reappeared in literature with very nice calligraphy. 18 years later, with the discovery of cheap four-color printing, the chart appeared in the book that Martin and I published in 1996, Gravity's Fatal Attraction. At this point, I should shamelessly plug the second edition of Gravity's Fatal Attraction, which has gone into production, I guess, as of yesterday or today, and should be available in a month or two. And of course, we've had to keep up with the times, so we're going to publish exactly the same flowchart, but in a more modern incarnation. It'll be really neat. It'll be like something out of Harry Potter. Okay. So what I want to talk about is the scenario of forming the seeds of supermassive black holes through some kind of large monolithic collapse process. And what that really amounts to is bringing gas together rapidly enough and in large enough quantities to form what was termed a supermassive star when they were first proposed, when these kinds of objects were first proposed 46 years ago. The idea of supermassive stars was actually proposed by Fred Hoyle and Willy Fowler back in 1963 as the energy source for, in fact, they were just before the discovery of quasars, so they were really trying to explain radio galaxies, which in 1958, Jeff Burbidge had shown must produce enormous quantities of energy because we saw the synchrotron radiation. And so Burbidge showed that in order to power a large radio galaxy, you had to convert the equivalent of millions of solar masses into the energy of relativistic electrons. They quickly converted it to a model for quasars, and the basic idea was simply to extrapolate the theory of stellar structure up to masses in excess of millions of solar masses. That means you're dealing with objects that are essentially completely supported by radiation pressure. Nevertheless, they do behave like stars because the burning of hydrogen, and in fact, it's really only the burning of hydrogen that can create a hiatus in the collapse of these objects. Can support them for a while. That can then be followed by some release of energy due to gravitational contraction. And then, in fact, they realized that these objects would be so unstable that eventually they must become black holes at least some level. They have very interesting stability properties because they are very close to gamma equals 4/3. They have equations of state that are very close to gamma equals 4/3, which you all remember from the theory of stellar structure denotes neutral stability against gravitational collapse. And so, in the simplest model, the very small residual gas pressure would have to stabilize them against collapse. This does, of course, make them quite susceptible to pulsational instabilities, but Hoyle and Fowler recognized that other effects realistically would help to increase their stability. For example, even a very small amount of rotation would make them much more stable. People later suggested maybe magnetic fields would help. And in fact, without either of those stabilizing influences, with just the gas pressure, supermassive stars can't exist at masses above about 1 million solar masses because even the small effects of general relativity, which makes gravity behave as if it's a stronger force than inverse squared, would destabilize it. It decreases the effect of, it makes the equation of state behave softer. But with even a small amount of rotation, these objects can be stable up to about 10 to the 9 or 10 to the 8 or 10 to the 9 solar masses. Okay, so that was the earliest version of supermassive stars. And to model these stars, Hoyle and Fowler recognized that when you have a star that's supported by radiation pressure with an energy source in the center, in order to support the entire star, the nuclear energy that's being generated in the center has to equal the Eddington limit for the entire star, because supporting something by radiation pressure means that your radiation force has to equal gravity. That means these stars radiate at their Eddington limits for their entire masses. You're only producing this energy, however, in a very small region at the center of the star that contains a small fraction of the mass, and therefore, to get that energy from the center to the outer layers, in fact, the stars have to be highly convective. So massive stars are essentially fully convective, and that means they're very easy to model. They are n equals 3 polytropes. They have equations of state where the pressure goes like density of the 4/3, and you can just write down the entire structure in a very simple form. However, Boyle and Fowler didn't ask how you could possibly form one of these objects. And since I'm worried about actually forming supermassive black holes from supermassive stars, I felt that I'd better ask this question. And for those of you who were born after 1970, that's Boyle and that's Fowler, Hicks' thesis advisor. Right? Okay. Well, growing a supermassive star is not very easy, because if you want to collect several million solar masses together in one place, you only have a few million years to do it. The main sequence lifetime of a very massive star actually does not depend on the mass of the star, because such a star has to radiate at the Eddington limit, which is proportional to the mass of the star. The fuel supply is also proportional to the mass of the star, and when you divide the two, the main sequence lifetime is a few million years. It's actually 2 million years if the star has a fixed mass, but if it's growing steadily, which I'm going to be proposing, you can get it to be a little bit longer. That means that in order to grow such a star, in order to have such a star, put such a star together before it runs out of fuel, you have to grow it at a large enough rate, which is about a fraction of the solar mass per year. Now, star formation that we know about does not occur at a fraction of the solar mass per year. When a molecular cloud condenses in the Milky Way, the m dot that forms the stars is about 10 to the minus 5 solar masses per year. And even during the epoch of population-free star formation, when you have rather dense gas clouds collapsing and forming massive stars, the rate is about 10 to the minus 3 solar masses per year. So you have to have an extraordinarily rapid collection of matter to form a supermassive star. But there's a second problem, which is that when we think of stars condensing, we usually don't worry too much about the Kelvin-Helmholtz time scale, which is the time for the star to thermally relax and come into a steady state. That becomes a problem when you try to create a supermassive star as well, because the optical depths are rather large, and the radii are quite large. And so the relaxation, in order for the relaxation time of a supermassive star to be shorter than the main sequence time scale, in fact, you have to have a star that is, if you can't have a star that's too massive, or it'll never relax during its main sequence lifetime. And that effectively puts an upper limit on the mass of a relaxed star of about 4 million solar masses. And so basically, the kinds of supermassive stars that we'd like to consider for forming these black hole seeds are not only difficult to grow in terms of collecting matter together, but also, in fact, they probably don't have time to thermally relax during their entire main sequence lifetime. And so the idea of assuming that a supermassive star has formed and then evolved is probably not the best way to think of the evolution of a supermassive star. Probably the entire lifetime of the star is spent in growing the star itself, and you have to consider the evolution and the structure simultaneously. There's another way of looking at this. If you have matter falling into this region here at the center of a protogalaxy and trying to collect together to form a star, it's probably coming in pretty fast. There's lots of shocks around, a lot of radiation is being created. Once that gas becomes too concentrated, the radiation that's created during the infold is no longer able to escape. It's dragged in bodily with the gas. That radius is called the trapping radius, and in fact, it's just proportional to the accretion rate. It's a few astronomical units for an accumulation rate of the solar mass per year. If you are steadily growing a supermassive star at a certain rate, if the radius of the star is smaller than the trapping radius, in fact, the radiation that's being brought in by the infalling gas can't escape in real time. It's perpetually being squashed by the new gas coming in. And so you can't have a supermassive star in an unrelaxed state that's smaller than its trapping radius. And so if we apply the theory of polytropes, we might conclude that the radius of a star with a certain mass is this value here. However, if that radius is smaller than the trapping radius, what the star is really going to look like is that. Okay? So the point is that you can't use polytropes and fully relaxed stars to model supermassive stars.
You think you can use spherical symmetry?
Probably not, but that doesn't matter too much.
Really? You are not wearing your disk hat.
I'm going to make one-dimensional models for these things. They're probably very, very thick disks.
Of course you
Yes.
are. Yeah, of
Okay.
course. Yeah, well, that's...
Okay. You can sort of graph all these things, and just to give you an idea of what the conditions on relaxation of these stars are, here's the infall rate, the rate of growth of the star on the x-axis. Here's 1/10 of the solar mass per year, 100th of the solar mass per year. As long as you're around 100th of the solar mass per year, there's no problem, but you can only build stars that are 10,000 solar masses before they run out of hydrogen. 1/10 of the solar mass per year, the stars are, again, fully convective by the time they reach their final mass of about 10 to 100,000 solar masses. But they're partly convective until they reach 10,000 solar masses, and so they don't relax until here. But once you get above there and you want to build really massive stars, then in fact, the stars never relax. Yeah?
So Mitch, I mean, although you're talking about supermassive stars, as far as I can see, most of what you said so far applies to any radiation-dominated stars above, say, 100 solar masses.
So it applies to VMOs also?
Absolutely.
Yes.
I can believe this.
Yes, and so I should have said that, that Bond, Garnett, and Carr also didn't consider the process of formation. No, just kidding. Bond, Garnett, and Carr, of course, considered the structure and evolution of very massive objects, VMOs, stars up to about 100,000 solar masses. And a lot of what I'm saying does sort of have relevance to that. But,
So in those days, the biggest issue was that there would be gigantic winds associated with instabilities, etc., and that would be the thing that would limit the growth.
Right.
So those were always our, I mean, to the extent that anybody dared to complain with our efforts, it
Right.
was associated with the fact that it's not at all clear that you would have a continuous accretion onto this, but that it would be turned around by the radiation pressure of the central stuff, and that there is a disconnect between the center and the outside that allows that wind
right.
to be a strong.
So probably these winds are never as large as the infall rates that you need to create these things.
And I don't deny that, but that means that you've made some approximations about continuity of your M dot star and all of that, and how it gets layered
Right.
on. Right?
Yes. Right. You might have winds. You might have stuff
Yes,
coming
yes,
into the
yes.
equator and going out the poles. But
We
nevertheless,
break the
the rate at
exactly.
which stuff has to come in the equator to build these stars is larger than the rate that you're likely to get mass walks out the poles.
Yeah, no, and so that's the
Okay.
breaking of the spherical symmetry here.
So just sort of to review the difference between supermassive star formation and ordinary star formation, ordinary massive star formation, let's say. Massive star formation occurs at less than a fraction of the solar mass per year. You then have a chance of getting a thermally relaxed object before it dies. The object can be fully convective, resembles a polytrope, and has a well-defined radius that is given by the usual polytropic formula. Supermassive star formation. Stars more massive than about 1 million solar masses require much larger accretion rates. Their outer layers are never relaxed, and so they must have a structure which has a convective core and a convectively stable envelope, which I'll talk about shortly. The radii of such stars does not depend on the mass of the star, but depends on how fast it's built up. Okay. This is the subject of trying to figure out the structure of one of these stars is really fun exercise in stellar structure theory. I'm not sure how much it really has a critical impact on the masses of the black holes that are formed, but I'd just like to say some things about what these stars are like. As Dick and Bernard know well, the entire key to understanding the history of a star is tracing the history of its entropy. And that's the case here as well. There is a remarkable property of n=3 polytropes that you can't make the entropy anything you want. For any other polytrope, you have a lot of freedom in setting the entropy. But in the case of a radiation pressure supported star, the only way to get a stellar model is to pick exactly the right entropy, or at least nearly the right entropy. And the value of that entropy depends on the mass of the star to the 2/3 power. Now, if you try to form a star with gas that starts out with extremely low entropy, very cool gas, and you sort of let it sift together, because it's radiation pressure supported, it's neutrally stable, it'll try to collapse in on itself, but then nuclear reactions start, push back, and if you start out with too little entropy, the nuclear reactions will generate exactly the right entropy, and you will reach a steady state for at least a while with this formula satisfied. But if you're building up a star by having gas implode at fairly high speed, which is probably how this all happens, the gas that you're trying to add to the star has too much entropy to be part of a stable star. So you can't regulate it by creating more entropy through nuclear reactions. You actually have to lose entropy. Well, that can also happen automatically, because if you have too much entropy, what it'll do is try to make the star explode. But if the star explodes, its optical depth goes down, it starts releasing radiation like crazy, and the entropy goes down, so it'll settle back, and it will also regulate at just the right value. Once the gas settles into the star, however, the radiation becomes trapped in the gas, and so you end up with a layered structure in which the entropy is not constant through the star, but it increases outwards, which means that the star is convectively stable. The ratio of pressure to density to 4/3 is proportional to the enclosed mass to the 2/3 power. And so it's a well-defined function of position within the star, and gives you a different kind of stellar model that you need to calculate. In honor of this bizarre equation of state, we figured we needed a Greek-based name, so we came up with helotropic or hylotropic, I'm not sure how to pronounce it, from the roots for matter and tropos, to turn, and we actually had a genuine classical scholar, Alice Accardi, help us with this etymology. She's married to Giuseppe Ludato, who's an astronomer. Now, the reason I'm worried about the pronunciation is that everybody so far has confused this with heliotropes, and I just want to point out that these are heliotropes, not hylotropes or heliotropes. I bet you didn't know that heliotrope was a 19th century instrument from the Royal Greenwich Observatory, as well as being a mineral, so it's not just a plant. You can work through the structure of these stars pretty straightforwardly, and I'll just say a few words about what the structures are like. This is the run of temperature in an N=3 polytrope, and you see it has a sort of a rounded core there, and then it trails off like this. If you try to match a heliotropic, hylotropic envelope to a polytropic core, it turns out that the match has to take place at a fairly restricted range of radii, within about 1 to 2 times the scaled radius, no matter how much of the mass is contained in the envelope versus the core. So these three curves are for 3 times the core mass, 10 times the core mass, and 100 times in the envelope. But the structure of the heliotropic envelope is very different from the structure of the polytrope. It's a much more extended body, and that, of course, has to be the case because these envelopes have to extend out to the trapping radius. They have to extend out far beyond the radius of the ordinary star. So these are much more bloated objects. Very roughly, the density goes like the radius to the -5/2 power. That's a very rough estimate because, in fact, it's not that much like a power law. And the pressure goes like the radius to the -3. Okay, so you can calculate these things pretty straightforwardly. There is also one important difference that is introduced by creating a model for the star that's only partly convective, and that is you no longer mix the fuel for nuclear reactions thoroughly through the entire star. You only mix it through the convective core. The convective core, of course, is growing with time relative to the envelope and eventually catches up. Well, it tries to catch up. It doesn't catch up to very large masses. But the fact that you have a restricted supply of fuel actually depresses the maximum mass that you can reach. And so this is probably a closer idea of what the maximum mass is. And so, for example, you could get up to 10 to the 7 solar masses, But in order to do that, you need about 30 or 40 solar masses per year.
Can we just take a numerical example?
Mhm.
Just choose a mass, let's choose 1 million, I don't know.
Okay.
So what would the central density be in range 360?
Central density for 1 million solar masses would be about the star would be at about an AU. So you have 1 million times the.
Wait a minute.
So it's about the same as the sun.
So it's 1 million AU.
It's
Now,
less than the sun. It's about,
you
about
were-
a
you were-
hundredth of a gram per cubic centimeter.
Maybe I wasn't being careful enough with my choices. So what we have is this convective core, and that's your MM, and you were dealing with numbers which were 100 and 1,000 times that.
Yeah.
Which means that you're going a really long distance
Yes.
before you get the turnout.
That's right.
So what sort of outside density, I guess that's what I'm really asking, how rarefied is the stuff out there that's accreting?
Most of the mass is still in the outer regions because the density.
Yeah,
drops
but
off.
that's because the radius is so big.
That's right. So
But
you're
I'm
having-
just wondering how, how.
the stuff that's accreting is very low density. It increases its density. It's coming in with very, very high entropy. And so when it settles onto the star, it increases its density by several
But
orders of
are we
magnitude.
thinking of something that's even in the outer, where the accretion is actually occurring? Is it a border ISM mean densities, or is it much higher, or?
It would be somewhat higher than that.
But only somewhat.
No, it would be quite a bit higher than that. I mean, you're talking about stuff coming in at a solar mass per year down to an
Yeah.
astronomical unit.
At what mass does the gravitational binding energy unit mass equal 790 eV?
Gravitational binding energy per unit mass.
Star.
I don't know offhand.
Well, because at some point, given your scaling,
Yeah.
the nuclear energy becomes a perturbation.
Yes.
Because R
yes,
goes as
that's a good point. I think you're well below that.
Okay.
Yeah.
How far? I just was wondering.
That I'm not sure. Yeah. Right. I mean, the interiors of these things are not that different from the interiors of ordinary stars, where the nuclear reactions are occurring. Yeah, and you know, I've worked out the nuclear energy generation rates and things like that, and yeah. So I don't think that's a problem. Okay, so that's sort of an introduction to what these objects might be like. But the objective of studying them, from my point of view, is to wonder about what kind of black holes are created. So yeah, first.
Just tell me, where is the Eddington limit on that graph? It's also a straight line parallel to.
The Eddington limit, the Eddington limit is reached at the radius of the star for these m dots. So you don't have to worry about the Eddington limit is not on this diagram. All these stars are at the all the stars that are partly convective are at the Eddington limit.
Eddington limit is m dot proportional to n, so presumably it's just.
I see what you're saying. No, the Eddington limit is m dot proportional to m times the gravitational binding, m dot proportional to m divided by the gravitational binding energy at the surface of the object. And so these objects are very large. So I mean, if you threw this much m dot into a black hole of 10 to the 6 solar masses, it would far exceed the Eddington limit. A black hole of 10 to the 6 solar masses can't accept 10 solar masses per year at the normal efficiency without exceeding the Eddington limit. But these objects are quite a bit larger than black holes, and so the radius of these objects is rigged so that the m dot just releases the Eddington limit when it hits the surface. That's actually how you calculate the radius, so it's all sort of self-consistent. Okay, so I know you're all waiting for the black hole to form, so we don't have to worry about all these stellar structure details. So how does that happen? Well, one thing you could argue is that the entire core of the star collapses to form a black hole. But that's probably not what happens. There's a small amount of, probably a small amount of rotation in these objects. In fact, if there isn't any rotation, then you have real stability problems. But also, the gas that's falling into these objects is going to have some amount of angular momentum, And even if the amount of angular momentum inside the star is rather small, when it collapses to form a black hole, unless it somehow can get rid of this angular momentum very quickly and before it falls very close into the center, there's going to be an angular momentum transport problem. And transporting that angular momentum outwards automatically implies that you're transporting a lot of gravitational binding energy outwards. And so the formation of the seed black hole from one of these big stars is probably regulated entirely by the transport of angular momentum, unless the rotation is very, very small, and that means rotational kinetic energy towards the center, about 10 to the minus 3 or 10 to the minus 4 Keplerian. Actually, the constraint becomes worse the closer in you get to the center. Okay, so if you do transport energy outwards as the black hole is forming, what that suggests is that the center of the star collapses first and grows only until the energy liberated in forming the black hole is comparable to the binding energy of the star just before the start of the collapse. Now, the binding energy of the star is very small because the star is radiation pressure supported. So the binding energy of the radiation doesn't contribute to the binding energy. It's exactly canceled by the potential energy. So the residual energy, if you forget about the relativistic effects, which would destabilize the star, the binding energy is just the residual gas energy and plus the rotational kinetic energy. And so the amount of energy liberated by a black hole, if it releases energy at 10% of mc squared, is only going to be a few hundred solar masses at the time that the first seed black hole forms. Okay. In forming a few hundred solar mass black hole, you liberate enough energy to basically blow the envelope apart. Okay. That's very small for a star like this because the core of the star is about 10 to the 4, 10 to the 5 solar masses. So only 1% or even a fraction of a percent of this core can collapse to form a black hole initially. However, you don't necessarily blow the entire star apart because unlike a collapse where there's all kinds of nuclear effects going on, the only thing that is releasing energy as the black hole forms is the infall of matter. So if you blew the whole envelope apart, the black hole would stop growing and you would stop blowing the envelope apart. And so what probably happens, I think, is that you essentially blow the envelope up, but eventually the rate at which the black hole grows drops to the point where, in fact, you could reach an equilibrium in which the energy released by the growth of the black hole becomes comparable to the energy that the envelope can handle, which is, in fact, the Eddington limit. So one way of looking at this is that initially, when the black hole starts forming, it's growing it's collapsing and releasing energy at a rate that far exceeds the Eddington limit for the envelope. That inflates the envelope. It would blow the envelope apart once you put in this much energy, but eventually the envelope grows to the point where it becomes leaky and can actually get rid of the energy that's liberated, and you can reach a steady state. So the steady state would, of course, have to be growth of the black hole at the Eddington limit. Okay, well, that's the way we normally think of seed black holes growing.
So that's true if you don't give
Yeah.
radiation. That's true if you don't give the energy a path to the outside.
That's true. You can increase the growth of the black hole. Yes, that's right. That's okay. I'm happy with bigger black holes. So let's just assume, I'm assuming that the growth is the Eddington limit in the sense that the energy dumped into the envelope equals the Eddington limit. And plus, if you can get rid of any excess energy some other way, that's fine. Okay.
So if I inject energy at the center, right?
Yeah.
So the energy is still less than binding energy. So how is that energy distributed throughout the entire source of the output? So it's starting to expand. Is it just convection?
Well, it'll be basically convection because basically you elevate the entropy at the center of the star to way above what it was initially. Then basically it drives.
So the core responds instantly.
Yeah.
Right, and then the envelope doesn't respond at all.
The envelope will respond on roughly a free fall time. It's very violent convection initially, and then it'll become more and more gentle as the entropy disturbance spreads out. Okay. Yeah.
I guess this is not the best time to ask this, but I'm a little worried about your assumption that this thing's only going by heating gas. In other words, material around it would be some mixture of gas and stars. And so one can ask, how sensitive is this picture to a small fraction of accretion in stars that are dragged in with the gas? I mean, beyond what point could you say if you had 1% of the mass composed of 100 solar mass stars that are being dragged in with the gas, does the whole picture change?
I haven't really thought about that, but I doubt it would be as much as a percent because I mean,
I'm just throwing out
Yeah.
a number. I think that then you have a 10 to the 4 solar mass, much denser object sitting.
yeah, that's possible. Yeah.
And I would think the structure then would change quite dramatically.
That's a good question. I don't know. This, of course, is all occurring within an astronomical unit at the center. So, I mean, you have to ask how many stars would have been dragged into within a few astronomical units.
But it's a quantitative issue. I mean, what fraction?
Yeah.
If you say you have a gas plus 100 solar mass stars, and that's, what's the maximum
That's
proportion
right.
that you could tolerate before the picture changes?
Yeah, that's I don't know. Yeah, that's something that should be looked at. Okay, so subsequent mass of the growth of the black hole occurs at the Eddington limit, but it's an important point that you calculate the Eddington limit correctly. Whose Eddington limit is it? Now, I don't want to take credit away from this guy, so that's not what I mean by this slide. But it's not the Eddington limit for the black hole itself that matters. It's the Eddington limit for the entire envelope. Because what's happening is the black hole is becoming the energy source for a star that basically consists of this bloated envelope. And when you have a very massive star, any very massive star, supported by radiation pressure, the luminosity of the star has to be the Eddington limit for the entire star, not just the core that's producing the energy. The same has to apply here. And so the black hole has to adjust so that it's radiating energy at the Eddington limit for a mass equal to the mass of the envelope, which initially is going to be maybe 3 or 4 orders of magnitude bigger than the mass of the black hole. Which means this black hole can grow at a tremendous rate. If a black hole grows at the Eddington limit, it e-folds in mass in about 40 million years with the normal efficiency factor. And so this would be 1,000 times faster than that, or an e-folding time of 40,000 years, or even less. So this 200 solar mass black hole that is the initial seed is going to rapidly grow to a much larger size. And the kind of object in which this happens is what we've termed a quasistar. It's supposed to be a star that's it's sort of like a Thorne-Chitov object, which is like a red giant with a neutron star at the center. But instead of a neutron star with nuclear burning going on at the surface, this is a convective envelope with a black hole that's accreting at the center. You can work out the structures of these things. They're sort of fun objects to think about. What has to happen is that the conditions in the envelope have to expand to the point where the accretion onto the black hole puts out just the Eddington limit for the envelope. That doesn't mean that the black hole is growing at the Bondi accretion rate from the inner part of the envelope, because in fact, what has to happen, you have an accretion flow that's not able to radiate effectively. And so what's happening is that the black hole is accreting. The energy liberated by the black hole has to go back out through the accretion flow. And so in fact, that puts a limit on how fast the accretion can take place, because the accretion flow has to be able to carry all this convective energy outwards. It limits the accretion rate to about the sound speed divided by the speed of light squared times the Bondi accretion rate. That's much lower than the naive accretion rate, but it produces enough energy to support these envelopes. And roughly the properties of the envelopes, they have central temperatures of about 1,000,000 degrees, so any nuclear reactions that were still occurring at the time this thing formed just stopped. The radius now expands from a few astronomical units to about 100 AU. So these are red giants that are 100 astronomical units across. What's that? Not all that much bigger than asymptotic giants, pretty big, but not outrageous. And of course, they become quite cool. And this goes on. Oh, yeah, and I should say, I sort of at various times I've regretted proposing the term quasistar, but I'm not sure we have a choice now because it already has a Wikipedia entry, which I didn't write. Although I checked it the other day and it looks like it might be removed soon because nobody has referred to this, so it might disappear, and then we can change the name. Anyway, also, quasistars are a pure mathematics term, and this definition has now jumped to the top of Google above all the pure mathematicians. So that shows you the power of astrophysics. So these objects get cooler and cooler as the black hole grows. The envelope continues to expand. But this can't go on indefinitely for the same reason that red giants can't be arbitrarily cool. You hit the radiation pressure-dominated version of the Hayashi track, and that limits the properties of these things. Unfortunately, for this type of object, hitting the Hayashi track is fatal. Okay. Just to remind you of what happens when you try to make a cold red giant, here is a typical opacity chart with density versus temperature. These happen to be for POP3, various POP3 abundances, but what I'm going to say applies pretty much regardless of what the abundance is. The kinds of densities you would find at the photospheres of a quasi-star fall in this band, and you see that there is a very strong temperature dependence below a certain temperature. For POP3 abundances, amusingly, the main opacity switches from Thomson to Rayleigh scattering. First it's Rayleigh scattering off atomic hydrogen, and then at cooler temperatures it's Rayleigh scattering off molecular hydrogen. And if you do a power law fit of the temperature dependence of the opacity goes roughly like temperature to the 13th power. So the temperature just plummets, the opacity just plummets below a certain temperature. What happens in, so the minimum temperature for POP3 is about a little less than 4,000 degrees. What happens when you hit the Hayashi track is if you try to make the temperature of the photosphere lower, the photosphere drops into the star and essentially decreases in radius so quickly that in fact it quenches the decrease in the photospheric temperature, and that's very nice. You get a unique minimum temperature for red giants. The problem is that if you try to do that in a radiation pressure supported star, you run into problems. In an ordinary red giant, you have radiation transport governing the loss of energy from the star, the leakage of energy from the star. You have gas pressure gradients governing the hydrostatic equilibrium of the star. You have enough degrees of freedom so that you can find a stable solution for the star even if you lose the ability to adjust the temperature. In a radiation pressure supported star, the leakage of radiation is still governing the energy transport. The leakage of radiation is also governing the hydrostatic equilibrium. If you hit the minimum temperature for a radiation pressure supported red giant and try to go below it, what happens is that you liberate so much radiation so quickly that despite the fact that the opacity is going down, you exceed the Eddington limit just below the photosphere. And so these stars have to disperse. And they would disperse almost on a dynamical timescale as soon as you hit this limit. You can calculate roughly the conditions for hitting this limit. It just depends on the conditions in the center of the envelope and how fast the black hole is accreting as a function of the density and temperature. And those are related to the mass of the envelope and the mass of the black hole. The bottom line is that a quasi-star disperses when the black hole grows to a couple of percent or a few percent of the envelope mass.
So for the quasi-star, the envelope is not convective.
The envelope is completely convective. It looks like a red giant.
I see. So, I mean, this partial convection.
No, that's before the black hole forms.
I see. So how is the partially convective envelope decomposed after?
Because the black hole in the center that's formed has now put out so much energy that it's completely dominating the entropy of the, Okay, so the bottom line is that the massive black hole you form, when you disperse the quasi-star, which is what I'm going to say is the supermassive black hole seed, is about 1% of the mass of the envelope at that time. You can turn that into an expression in terms of the infall rate. It's about 30,000 solar masses times the infall rate to the 7/9 power, very roughly. So you can get black holes of a few tens of thousands to maybe 100,000 solar masses for this process, which is a pretty good start for a supermassive black hole. Okay, I want to conclude by just briefly talking about two aspects of this model. First is whether these supermassive stars and their products can be detected. Just before the black hole forms, when you have this partially convective supermassive star, you have something that's actually pretty hot. It's going to be a good ultraviolet source, radiating about as much as a Seyfert galaxy. So it might have an interesting effect on ionization, reionization. I'm currently trying to work on that with Marta Voluntary, so I can't give you any numbers about that. Obviously, you'd have to know how many of these things there are. It's going to be hard to distinguish from clusters of hot stars. However, immediately after the black hole forms and you get this inflation into a quasi-star, you're dealing with an object that looks completely different. It's going to peak in the optical IR. From the point of view of flux alone, it turns out that these kinds of objects might be detectable with JWST. That would certainly be the instrument to use to look for them. If they form at redshifts of about 6 to about 10, actually, they're a little bit more massive, maybe a redshift of 15 or 20. Their fluxes fall into the range that JWST is supposed to be designed for. At those redshifts, they're going to peak at about a few microns. And so you can sort of get a picture of where they fall relative to the sensitivity of JWST. If you look for the peak of the black body, they're up here, so they sort of fall below the line for photometry. I don't know how up to date this is. I pulled this off the web a couple of years ago, so maybe things have changed. If you look a little bit harder than the peak of the black body off on the Levine tail, you might even have a better chance of detecting them. But of course, detecting them, if you know where they are, is very different from identifying them, and I think that there's a lot more work to be done to figure out whether there's any real chance of identifying these things. They're going to look like a lot of other objects, especially if they have very low metal abundances and you can't get any redshifts, or if they're not in objects where you get absorption. But, yeah?
So what you would observe is when the time when the envelope gets blown away, or is the like?
Well, no, you would see them during the time that they're inflated into a quasi-star, but before they get blown away. That era would last maybe a few million years. Just doing some rough estimates, if you have one of these per L-star galaxy, I think, and then take into account the fact that they're short lifetimes, you still have about one per JWST field. But there could be more than one per JWST field because you would get mergers of these objects later on. Yeah.
Mitch, are you envisaging there being one of these objects a galaxy, or are you envisaging the more exotic sort of scheme with Ostrich and Canadian ones, which you've got halos with these quasi-stars?
I don't know yet. Mark Voluntary and I are running merger tree calculations to try to figure out, putting in models for the preconditions necessary to form these things, which is what I'm going to talk about next, to sort of see how many there are. But it looks like they're not, if these things can form at all, there may be a fair number of them, more than one per L-star galaxy. You could to produce all of to seed all the black holes, of course, you only need one per L-star galaxy. But since each of these is much less massive than a current day black hole, you could have more than that.
Yeah, but the Ostrich wanted to have 100,000.
These would have to form at the centers of halos which are already fairly massive. And so I'm guessing that that's unlikely. They probably have to form at the centers of halos that are more than about 10 to the 8 or 10 to the 8 or 10 to the 9 solar masses each. So relatively rare, the more massive satellites at a fairly late stage of galaxy formation. I think Ostricher's black holes would probably have to form in much smaller objects to be as many as he wants. Yeah, so that's what I think the answer would be to your question. Okay. The final thing I want to talk about, if I just have a few minutes, is the question of whether you can actually, where and if you can find the very large infall rates necessary to create these things in the first place. The fastest rate you can have gas infalling is the rate that's associated with the gravitational collapse of a self-gravitating object. Okay? So that means that if you have an object with a certain virial velocity, virial temperature, associated virial temperature, The natural gravitational infall rate, the one that determines the rate of star formation in the present-day universe, is that virial velocity cubed divided by g. And so to form an object like this, which requires mass to come together at greater than about 1 solar mass per year, you need objects that have virial temperatures that are significantly above about 10 to the 4 K. Okay? So these things can't form during the top 3 era. They can only form at a much later time when you have these much larger halos. Of course, in having any gravitational collapse problem occurring on a dynamical timescale, you have the problem of how you get rid of the angular momentum. Well, that's something I'm not quite as worried about as many people seem to be, because if you have an object that's self-gravitating and has a significant angular momentum, then such objects are very unstable to forming bars, basically to becoming non-axisymmetric. They develop very strong gravitational torques, which can get rid of the angular momentum on a dynamical timescale. And so if you can set up these conditions of self-gravitating clouds with such large virial temperatures, probably they will just basically collapse on a dynamical timescale. The other problem, however, is whether such objects simply form stars, because these objects, being globally gravitationally unstable, if they cool to well below the virial temperature, they probably become even more violently unstable to local gravitational instability. So why don't they just form little blobs that then cease to do much? They won't develop large-scale gravitational torques. They'll simply heat up into basically spherical star clusters. Well, I was very worried about this when we first started thinking about this, and in fact, we proposed in our original paper in 2006 that this whole process would be limited to systems with such low metallicities, even at redshifts as late as 10 or 12, such low metallicities that in fact you couldn't get the gas to cool, and such low molecular hydrogen abundance that you couldn't get the gas to cool below about 10,000 degrees. And so that seriously limited the number of these systems that could form. However, I am no longer sure I believe that, because all the simulations I've seen lately, including the ones by Robin Levine, do not show the evidence for wide-scale, large-scale fragmentation that you might expect from a simple estimate. Now, just to sort of graphically show how this gravitational infall process gets underway, here's a dark matter halo with gas. If the gas cools to a little bit below the virial temperature, it will shrink like that. That increases the relative importance of any rotation that's present. And if the rotation becomes significant enough compared to the other forms of energy, you get large-scale instabilities which lead to infall. And I won't, because of time, I won't show a little movie I have of that kind of thing happening. What I want to show is some results of recent simulations by Wise, Turk, and Abel, which show, in fact, that what seems to happen in the simulations that have been done is very similar to simple analytic models. You basically get the gas developing a profile of a singular isothermal collapse, which means the density goes like radius to the -2, and there it is developing over time. It goes down over an enormous range of radii. It shows evidence for the scenario of multiple global instabilities occurring in a hierarchical nested way, which we call bars within bars. So what happens is the gas becomes self-gravitating. This basically maps a criterion for the gas to become globally unstable to the formation of non-axisymmetric structures, sort of McLaurin spheroid type of instability. And you can see basically that the thing bounces around below the stability threshold and then every so often jumps up above it. Every time that happens, there's a large-scale transfer of angular momentum and the gas shrinks down to the next size. And so although the averaged density profile is remarkably close to a black body, the whole process is very intermittent and really does seem to be one in which you sort of have a structure that's sort of more or less axisymmetric. All of a sudden it elongates, gets rid of its angular momentum, moves in by a factor of 6 or 10, does it again.
And
Yeah.
this is by, this is clearly shown in the simulations.
Yeah.
And how many simulations do you have? I mean, it really is episodic.
This is,
And in episodic, is it got a, you know, a theory behind it, or is it just a random number of when it happens?
this is something we don't quite know yet. This is, when you say a lot of simulations, basically I know 3 sets of simulations.
Oh, yeah.
So this is something that has not been studied systematically. It's just something that's giving us hope. Okay. But the thing that surprised, none of this surprised us because, of course, I was suggesting bars within bars a while ago. It did surprise us that anybody found anything that remotely looked like this. One thing we did not anticipate, however, is that this seems to be accompanied with a very high level of turbulence, in fact, a supersonic level of turbulence. And so although this gas the gas in these simulations, in some cases, is much colder than the virial temperature, and you would think it would be violently unstable to local gravitational instabilities, which would break up into fragments. In fact, you're developing enough turbulent energy so that its temperature is not as small as you think. And you can sort of take this turbulence into account in a very crude way by considering these collapsing gas clouds as kind of tomb ray disks, but with self-similar contraction, and treating the turbulence as a thickening agent to make it so it's a sort of a tomb ray type of criterion, but considering the finite thickness of the disk, which weakens the tendency of the disk to fragment. If you do a pure tomb ray criterion on one of these disks, this vertical line in each of these panels is the criterion for global gravitational collapse, bars within bars. If you do a tomb ray criterion, you predict the thing fragments, because it goes unstable to fragmentation before it goes globally unstable. If you take into account this turbulence that is observed, it turns out that it's much more unstable to global effects than it is to local effects. So you would predict that in fact the disk could completely collapse without being unstable to fragmentation. And so that's sort of the rough argument. But this does need a lot more numerical study. If you can avoid fragmentation, then there are plenty of places where you could have situations where supermassive stars, in principle, could accumulate. Anytime you have a protogalaxy with a virial temperature greater than about 10,000 degrees, which means a mass of more than 10 to the 8 or 10 to the 9 solar masses, those kinds of objects would become fairly common at redshifts of about 12 to 15. And so, in principle, you could have these objects forming pretty commonly at that epoch. Well after the POP3 star formation era, but with forming black holes that start off large enough so that their masses could quickly overtake any black holes that are growing from the mergers to POP3 and accretion onto POP3 stars. You see infall rates of this kind of magnitude in simulations of mergers, of halos that are much more massive than this. Obviously, if you set off this self-gravitational infall in a modern-day galaxy with a velocity dispersion of 100 kilometers per second instead of 10, you could get infall rates of about 100 solar masses per year and form a really big supermassive star, in principle. And you see these kind of infall rates in simulations, for example, of the kind done by Hernquist and Springle and Di Matteo, although, of course, these simulations are under-resolved at the small scales you need to actually figure out what's happening in the center. And if both of these arguments fail, which sometimes they do when I try to convince people, I just say that, look, quasars are fed at rates of a solar mass per year or more. We know that somehow happens, so it has, just imagine a quasar but with the black hole missing. The gas that's coming in to feed the quasar is coming from a much larger galaxy with a much larger mass, so it presumably does not know the black hole is there until it gets fairly close. So somehow these infall rates are possible down to fairly small scales, and therefore it's not too unreasonable that this can happen because quasars do it all the time. Okay. So I already gave my mea culpa, which is that I'm no longer convinced that you need metal-free gas and suppression of H2 to get these very large infall rates. So let me just go to the conclusions that I've just argued that if you can somehow arrange for very large infall rates of gas into the centers of potentials, you can produce supermassive stars that eventually leave behind black hole seeds that are quite a bit larger than the kind of seeds you can get from top 3 stars, perhaps 10 to the 4 or 10 to the 5 solar masses. One of the phases in this process is the formation of a gigantic red giant type object, which might be detectable with JWST. Such a process could occur in principle at much lower redshifts, although, as Chris pointed out, if you have a lot of stars present, you do have to worry about how they affect the process. I am no longer convinced that rapid self-gravitating gas of even very cold gas leads to widespread fragmentation. I think that is a crucial problem that needs to be studied with much more carefully controlled numerical experiments. And if you can form these large seeds, even at a redshift of maybe 10 or 12, provided the seed black holes start out off as large as 10 to the 4 or 10 to the 5, you probably have plenty of time to grow 10 to the 9 solar mass black holes by a redshift of 6. Thank you.
Would your model actually predict the large price factors of these quasistars?
Maybe. I mean, they would predict you tend to form these where you can have very large infall rates first. So those would presumably
These are the
that would
largest
presumably
scales
bias
at
them.
this time, basically.
Sorry.
These are the large scales at this given time here.
Yes. Yeah. And so, I mean, I've been thinking of ways you might identify these with JWST, and so one way to do it might be to identify early clusters, proto-clusters of galaxies, and then look for these very red objects embedded in them. And hopefully there will be some kind of absorption lines which you can use to identify get redshifts.
So the quasistars are only very short-lived, a couple of million years.
Yeah.
Do you actually see enough in JWST to find them?
Well, that depends on how many there are, but even if there's only one per, I have some slides which give their possible abundances, but I'm reworking that now because we're relaxing the constraint on metallicity, but increasing the constraint on the m dot you need to form them. So I don't know what the trade-off is going to be, but it looked like you wouldn't have too much trouble getting one per L-star galaxy, which then gives you about one per JWST field, if they occur at low enough redshifts.
But that's the logic at the end of the day. So you can increase the mass accretion rate using m of the star instead of m of the black hole. But then normally you would say, well, but Eddington is the scale invariant problem, so at the surface of the black hole, you're still limited by m dot Eddington of the black hole itself, but you say you get around it because you can add pressure of the star to the electrons going into the black hole, right?
No, you're not necessarily limited by the Eddington limit of the black hole itself. This is very similar to the problem of non-radiative accretion flows, which you can scale up to any m dot. What happens when you have a non-radiative accretion flow is that you probably have a huge amount of mass loss, so you only accrete a small fraction of the mass that's supplied at very large distances. But you can scale that mass supply up, and if you do that, you increase the accretion rate onto the black hole. What happens when you have very super Eddington accretion is that the radiation that's produced does not escape. It's stuck in the gas. And so the luminosity, the diffusion of the radiation through the gas does not necessarily exceed the Eddington limit. The rate at which energy is produced exceeds the Eddington limit, but that's no different than saying you have accretion onto Sag star, which is presumably producing a lot of thermal energy, and very little of that thermal energy is getting radiated away. Same thing happens if you try to have super Eddington accretion into a black hole. Suppose as long as you start with a large enough m dot at large distances, you can still have the black hole swallow as much as you want.
But then you don't even need the star if you have non-radiating accretion. There is no Eddington limit.
The problem is if you don't have the star, then eventually you reach a boundary condition very far from the black hole where you blow away so much material so that you regulate the m dot at less than the Eddington limit. So it's I guess you're right that it is the pressure of the star at large distances that allows you to accrete more. Yeah.
So I want to go back to this issue of the utility of turbulence for doing wonderful things. Turbulence can, with gradients, presumably do very efficient transport as well. surely that is probably as dominant as any of the other effects you talked about.
Probably, yeah.
Has that actually been modeled numerically very well? I mean, usually people do turbulence studies in a fairly straightforward environment, although I might look back at a certain individual who's probably got this completely nailed. What's happening?
So in our simulations, we did end up finding that viscous transport was less effective than gravitational torques. So, I mean, it was certainly happening, but it was not as strong an effect as.
But how well were you set up for having the large dynamic range of turbulence being treated?
Well, it's a little tricky to be sure that we had a large enough dynamic range, but I think we did. I mean, we were resolving scales where it's isotropic.
It would seem to me that there's a sequence of studies to do, just trying to focus on the turbulence
Yes,
itself.
I agree. The dynamic range of these simulations for resolving turbulence is not all that great. It's like typically a factor of 3 or 4 or something like that. One thing that did worry me was the residual rotation that would be left in this flow and whether it would sort of disappear when the thing would go into solid body rotation. So I read some of Matt's papers, and that convinced me that he couldn't say anything. That it could have all kinds of bizarre rotation curves.
But
And so
probably
that-
not solid body. You can
Right, and that was one thing which is was good from my point of view. Yeah.
So are bars within bars giving you this factor of 10 enhancement? Because if you go back to your D turb cubed over G number, that gave you 1/10 of the solar mass per year. So you're getting stuff through the disk at a factor of 10.
No, so basically you need a larger variable temperature than 10 to the 4. It goes up as T to the 3 halves. So to get 1 solar mass per year, you actually have to go up to about 30,000, something like that. 20 or 30,000, yeah.
So supersonic turbulence, I know it sometimes exists in cases where the alpine speed is bigger than the sound speed, but I think you were showing something what's happening for a different reason.
Here basically what's happening is that the energy is being pumped into the turbulence faster than it can decay. The decay time is the dynamical time, and the turbulent energy is building up on that time scale. So, I mean, this whole thing is falling in on the free fall time scale. So I think what's happening here is just that the turbulence doesn't have time to decay, and it's energy is being pumped into it really, really fast. So that's all I think is going on. So that's why, I mean, I was surprised that seemed to be what happening in the simulations. Does definitely need to be studied more systematically. Chris?
So, by your argument that the super radiation accretion is like a non-radiative flow, but with outward conductive luminosity, there should be a CDAP at the center of the flow, surrounded by a self-gravitating CDAP. Is that part of the model?
Well, that's how I got the accretion rate to be this small fraction of bonding. What you need is you need the inflow rate to be small enough so that the outflow rate of turbulent convective energy does not exceed the saturated value. Now, whether this is a CDAF, where it's sort of a local balance between liberation of gravitational energy and outward convective flow, or whether it's more like an adios, where you have a zone going in and a zone going out, I don't know. But I mean, it doesn't really matter because all that matters is the overall energetics. It might matter for the question of whether you have an outlet through a jet or something like that, and it could well be that these stars have a funnel, and they're sort of like perpetual gamma ray bursts, and you lose a lot of this energy, and then you could grow bigger black holes. If that happened, then you could get even more going into the black hole. Yeah.
Is there any reason you would expect black holes less massive than about 1 million solar masses to form? I mean, is there any cutoff?
Well, the cutoff comes from the fact that if you have an efficiency of energy release of about 10% or something like that, or even a fraction of 10%, you puff up the envelope to the point where it crosses this opacity crisis line, and the envelope blows away. And that happens when the black hole's about 1% of the mass of the envelope. And so, the supermassive star could get up to 10 to the 7 solar masses, or maybe a few by 10 to the 7. It can't get much more massive than that, or else you have all kinds of other problems. Although, I suppose if you ended up with the GR in general relativistic instability taking over, you could get a collapse of a much bigger black hole.
I guess the question really was, would you expect a bunch of 1,000 solar mass or 10 to 4 solar mass black holes kicking around by its
Oh,
position?
could you do this? I guess you could form smaller black holes if something interrupts this process. First of all, it's going to be limited by the infall rate. It's going to be limited probably by mergers or other disturbances, or maybe stars putting in extra energy and blowing away the envelope. So there's all kinds of things that could interrupt this. So in a sense, what I've discussed is maybe a sort of a maximal effect. Yeah. So yeah, you could have more of these, I suppose. Very good.
I'm still not quite certain what the lower limit is for which this model is going to work. You said 10 to the 4 solar masses as your conclusion, but how lower mass can you go to and still apply this sort of model?
Well, I mean, if you are happy with, I think you could go to, if you could actually do something like this in a with lower infall rates and end up maybe with 1,000 solar mass black holes. Yeah, I mean, perhaps you could use this process to get smaller black holes, but then you start to sort of get into the realm of ordinary stellar mass black hole formation that you would expect from top 3 stars. And you expect probably a fair number of 100 solar mass black holes from the first generation from top 3 stars.
I was just interested in whether you could apply this model to a small scale thing.
Yeah, I think you can scale it down, and of course, if you scale it much below 1 million solar masses, then you end up with a relaxed object, and you can just use the usual theoretical models. And then, yeah, you can also have quasi-stars forming, which are just 10,000 solar masses. Yeah.
Okay,
So I think you kind of scale it down.
So, is there any more questions? All right, if there's no more questions, thank you, Mr. Jan.